going to start by introducing Professor Frank. So Professor Frank Piessens is a full professor in the Department of Computer Science at the Catholic University Leuven in Belgium. So his research field is software and system security. He has worked both on attack techniques as well as on defenses. On the defense side, he has contributed to the verification techniques for C-like languages, the enforcement of information flow security, the countermeasures for memory safety related vulnerabilities, and the design and implementation of embedded security architecture. On the attack side, he has contributed to the discovery of several transient execution attacks and to the development of exploitation techniques for memory safety vulnerabilities. Frank has served on the program committee of memory security and software conferences, including the ACL, CCL, UNIX, IEEE, SMP, ACM. He acted as program chair for the International Conference on Principles of Security and Trust, post 2016, for the IEEE European Symposium on Security and Privacy, 2018-2019, and for the IEEE Secure Development Conference, SecDev 2021 and 2022. I'd like to thank you again, Frank, to be between us today. And
thank you very much, Dr. Uni, for the introduction, and thank you very much for the invitation. I'm honored to speak at the Technology Innovation Institute. This seems to be one of the rising stars among research institutes worldwide, and I heard it's growing fast. So it's a pleasure to be here. So this talk will mainly be about the class of attacks and corresponding defenses that exploit optimization techniques in processors. And more specifically, I will focus on what are called transient execution attacks, and I will try to make the talk interesting both to people with no background on these attacks. So the first part of the presentation, the modeling transient execution attacks here, really the goal is to explain transient execution attacks from first principles based on a simple processor model. But I'll also try to make the talk interesting to people who do have a bit of background on these attacks, and that will be the second part, where I'll talk about defenses. In particular, in the last part of the talk, I'll talk about a very new defense, the prospect defense, that my own team has developed and that just got accepted to Usenix Security 2023 a couple of weeks ago. So this is an example of a state-of-the-art defense against these attacks. So I hope that by serving two audiences, I had no idea who would be in the audience here. I hope there will be something for everyone. In any case, do not hesitate to ask questions or interrupt me if I go too fast or if things are not clear. I'm very happy to be interrupted and try to answer you.
So just I want to for the audience use the question and answer section to ask, and then I'm going to answer it. Fine.
Yeah, okay. So I may not be, if you type in the chat, I may not see it, but Dr. Uni will interrupt me.
No worries for that.
Okay, thank you. Okay, so let's start. So on the slide here, you see like a very high level system model of the kind of systems that we will consider in this talk. So what you see here is some kind of computation platform, I think a processor, maybe with some system software on top of it. And that processor is used to run code from multiple stakeholders. So we will have some of these might be victims, some of these might be attackers. So we will have code from multiple distrusting stakeholders running code on that same platform. So that the prototypical example to keep in mind is this is a server in the cloud, for example, and then you will have multiple virtual machines belonging to different stakeholders, and what we want to consider is the possibility that one of these stakeholders is malicious and wants to attack one of the other stakeholders that will then be the victim. Now, what else is important? So we will consider a scenario where according to the specification of the processor, according to the machine code, the assembly language specification of the processor, we call that the instruction set architecture or the ISA specification, the various stakeholders are isolated. So for example, they might be running in different virtual machines on the cloud, or there might be different processes on your desktop, or there might be different tabs in your browser. So the attacker and the victim, the two pieces of software executing on the platform that might want to attack one another, are at the level of the instruction set architecture, at the level of how the processor is supposed to work, are isolated from one another. They can't interfere with one another. But typically, a processor is implemented itself as a very complex beast. So a processor has additional state, things like caches, branch predictors, reorder buffers, and so forth. And these, we call these microarchitectural resources. These microarchitectural resources that are part of the processor are sometimes shared between code even belonging to different stakeholders. So even if you have two different virtual machines on a cloud processor, they might still share certain of these microarchitectural resources. And the general problem that we want to look at is, can an attacker rely on that? Can an attacker use that? Can an attacker exploit this kind of sharing to learn what the victim is doing? So we worry about information flows about what the victim is doing to an attacker because of the fact that these microarchitectural resources are shared. That's the very big picture of the kind of problem that we want to look at. So this problem has been known and has been relevant for a while. So for instance, cache attacks, I won't talk a lot about cache attacks today, but they've been known for close to 20 years now. There are good surveys of the different attack techniques. We also already understood for a while how to deal with them. For example, cryptographic software very often is developed to be resistant against these kinds of attacks, and a typical countermeasure there is the constant time programming model. I'll mention a bit about that later in the talk. So this was a well understood problem up until about 5 years ago, and then 5 years ago, transient execution attacks, the attacks that I want to talk about in this seminar, came on the scene, and they kind of changed the game very significantly. Attacks like Spectre, Meltdown, and Foreshadow, these were the three first, all publicly disclosed about 5 years ago. They showed how a particular processor feature, a speculative and out-of-order execution, how this feature significantly amplifies this problem of microarchitectural attacks. And you see the papers on these attacks. Unfortunately, it was not just three vulnerabilities or three specific attacks that could easily be fixed and then we could move on. Many other variants followed, and over the past years we've seen a whole plethora of attacks, and the impact of these attacks and the development of the corresponding countermeasures has had a strong impact both on academia and on industry. And I want to illustrate these 2 points very briefly. So first, the fact that you have many variants. What you see here on the slide, and I don't want to discuss it in detail, is a classification tree taken from this paper and further maintained at this website. And I don't want to discuss the tree in depth, that would take too long. But the point I want to make is every red leaf that you see here, each of these red leaves represents one variant of a transient execution attack. And I'm just showing you the tree to show that this is a whole range of problems. It's not a simple problem or a single problem that we can solve with a single patch. Right? Second thing I want to briefly illustrate is the impact. So these attacks are less than 5 years old, well, about 5 years old now. And to give you an idea of academic impact, here you see the three first papers, Spectre, Meltdown, and Foreshadow. Together in these 5 years, they have gathered more than 5,000 citations. So that's an enormous indication of academic impact, I would say. Also on industry, if you look at, for instance, CVEs, so vulnerability disclosures, there have been more than 30 in the past 5 years. And if you look at the effort that companies like Intel and Microsoft, or ARM and AMD, or the Linux kernel developers have done to kind of mitigate these problems, then if you look at that, I think you can say that the impact on industry has also been huge. So with that, I hope I convinced you that these attacks are interesting to look at, interesting to study. And so the first thing I want to do is kind of build a model, a simple model of a machine that we can use to then study first attacks and then defenses or countermeasures against these attacks. Okay, so I'll first build a model, and the first thing we need is a simple instruction set architecture. Think of this as machine code or assembly language code for a processor. And I'll use MicroASM, which is developed in some papers that I'll give references to later in this talk. So this is a simplified machine code that makes it easy to reason about programs in assembly language and makes it easy to give examples of these attacks. So this is the language I will use. Here is a full definition. In this machine language, in this assembly language, we will have registers, a finite set of registers, and we'll give them any name we like. So here are some names we could use, but we will use any name we like. The values that this language computes on are natural numbers. We could also use things like 32-bit words or something like that, but for simplicity, we just pick natural numbers. And then one simplification with respect to real machine languages is that we will allow arbitrary complex expressions, so we can write values or registers or any kind of operation on them, addition, comparison, multiplication, whatever we need. By allowing that, we can do with just 5 instructions in the machine language, which makes the language a bit simpler. So the only 5 instructions we need are an assignment instruction, which computes an arbitrary expression and stores the result in a register. Then load and store instructions that will compute an address in memory and then either load from that address or store a register at that address. And then control flow instructions. We have a compute a jump where we have an expression that can compute a code address and we jump to it. And we have a conditional branch. This instruction will jump to address V if the contents of address of the register R is 0. This is a branch if equal to 0 instruction. And this one is actually not essential. We could actually compile it to this one, but it will be useful to have in examples. So that's all we have in terms of instructions in this language. And a program is then just a list of instructions. And I hope if you've ever seen any machine language like x86 or RISC-V or ARM, this language will be easy to read for you. Just to show some examples, here is one program that implements this while loop. So this while loop computes the sum of the first 2 elements in array A. And you see that the first thing we do is we compute the loop condition. And if it's 0, which means false, we represent false as the number 0. So if it's 0, the loop is done. We jump to the next instruction. And while it's true, we execute the body of the loop and we jump back. Right. So this should be not surprising. If anything is unclear about this, you're welcome to ask questions. But if you've seen any machine language, I think this will be easy to understand. So here is an example where if we start this machine in a state where program counter and registers are all 0, we have these 4 registers, for instance, and we start it with memory containing these 2 values at the addresses 0 and 1, then what this program would do is compute the sum of the first 2 elements of array A, which points here. So that would be, it would compute the sum 9, right? So let me walk you through that execution just to show how the processor executes. And we can actually make this a fully formal semantics. I'm not going to do that in this talk, but I hope you'll see when we go through the example that making this completely precise is really just a small step. So how do we represent the state of a running program? So the state of a running program consists of a memory, which is just a list of values that we index into with natural numbers as addresses. We have a register bank row, which is just a mapping of register names to values. And we have a program counter, which is the counter to the current instruction in the program. Okay, and here you see an example, again, the same program we saw on the previous slide, a memory and a register bank and a program counter. And now here you see an actual execution, and let me walk you through the first 1 or 2 steps. So how does the processor operate? It gets the instruction at the program counter address. So in this case, instruction 0, it fetches instruction 0. It computes this expression, which will be true, because 0 is smaller than 2, so it's 1. So it will assign 1 to R0, you see that here, and move the program counter up, and then we are in this state. And now we have executed one instruction. And the next instruction is we fetch this instruction. This is a branch if equal to 0, so we check is R0 0. It's not, so we just fall through. The program counter becomes 2, and the registers don't change. Okay, let's do one more. So this is a load. A load means we have to compute the address of the load, a plus I. A plus I is 0. We take the address 0, we go to memory. We find the number 5 there, and we put it in register R0. Right. So, and then we are in this state, and so forth and so forth.
Right? One question here. The
yes.
question is, condition execution would always be represented as a succession of at least 2 instructions here.
Sorry, I'm not hearing you very well.
Yeah, conditional execution would always be represented as a succession of at least 2 instructions here.
Yes, so conditional execution would you typically use this conditional branch instruction. You could also have conditional execution using the computer jump, but I'm not using that in this particular example. Did I answer the question with that? I'm not sure I completely understand.
I think yes, but if I have another.
So what we don't do yet here, I'll come back to that later, is speculative execution. We don't have that yet. I'll come back to that later.
Thank you.
Okay, so this is really just the architectural semantics of a very simple machine language, and you see that if we would continue this execution, I'm not going to go through all the steps, that indeed at the end we have computed this sum 4 plus 5 correctly. Okay, so let's see. I think that's all I want to say about the machine language.
One more remark. I mean, they said like that. But conditional execution in ARM, for example, checks the whole states register, not just EQ there.
Yes. So this is not similar to conditional execution in ARM. So conditional execution in ARM you can use to kind of either execute or not execute a register, an instruction based on a certain register or bit or whatever. This is really the conditional jump as you have them in all assembly languages.
Okay.
Okay, does that answer the question?
Yeah, thank you.
So I know that conditional execution as in ARM is sometimes used also as a countermeasure against microarchitectural attacks, but that's not what we'll model here. So you'll see that this is really any assembly language. We don't need the notion of conditional execution or data independent timing instructions and so forth, like you have that in ARM and also in some recent Intels. This is really just standard ISA, to which I want to add speculative execution later to specifically deal with these new transient execution attacks.
Okay.
Okay, so I said when we discussed the system model, I said that we think of architectural state as securely partitioned. So for instance, victim and attacker are in different processes or in different virtual machines, right? So in this model, the way in which we render that is the program that we have, any program running on this processor, you should think of it as having completely separate program states. So they have different memories, different register banks, different program counter, and so forth. And when I show you a program, it will usually be a victim program. And then the attacker program would be something completely different that can't interact in any way. There's no way even to write in the language a way in which attacker and victim could interact with one another. That's on purpose, because the attacks that we'll consider do not exploit any kind of sharing or communication at the architectural level. They all exploit microarchitectural channels, right? So you might wonder then, if all we can do in this language is write a victim program, how can we then reason about the attackers? I'll come back to that later. So that's a very good question, but at the moment we can't reason about attackers yet. I'll come back to that later. Okay. So what do we need in addition? So far I just have basic assembly language. So of course, in order to study these transient execution attacks, we will need out of order and speculative execution, right? So let's add that. And at a very high level, what does out of order and speculative execution do? The very high level idea is, rather than fetching instructions at one at a time, like we did when we did the example execution a couple of slides back, with speculative execution, you fetch many instructions at once into a buffer that we call the reorder buffer, and we call these instructions in the buffer, we call them in-flight instructions. And then in this buffer, the processor can execute the instructions in any order that makes sense. And what that means is any instruction that is for which all dependencies are satisfied, that's ready to be executed, can execute, right? It doesn't have to be in program order. But the execution of these instructions in the buffer remain in the buffer. They're not yet visible to registers and memory. That's a separate step that we call a commit step. So when the oldest instruction in the buffer is done, the processor can commit the results of that instruction to registers and memory. And I'll give a detailed example on the next slide. The final point I want to make in this big picture is that, of course, if we want to do this, fetching many instructions and executing them out of order, we will need prediction and speculation. Why? Because if you fetch instructions and one of them is a branch, then we will not know whether that branch will be taken or not. We are not yet at that point in execution. So if we want to fetch many instructions, we'll sometimes have to speculate where control flow will continue. So for instance, we might have to speculate whether a branch will be taken or not. Okay, so we'll have to build that in, and as a consequence, the execution will sometimes be become non-deterministic. So let's look at the details. So I will extend the model that I discussed with out of order and speculative execution now, and the extension is actually relatively simple. So in terms of program states, we still have a memory, a register bank, and a program counter. That's exactly the same. The only thing we add is this reorder buffer. And this reorder buffer is really just a list of in-flight instructions. And in-flight instructions, for the moment, think of them as just instructions. They're a bit special, but I'll explain what's special about them when we go through an example. At first approximation, you can think of them as just machine code instructions. So let's look at an example execution. Here is a toy program that I wrote, and we'll walk through an out of order execution that also uses speculation, just to show you how the processor works. So here we see the processor in its initial state, all register 0, reorder buffer empty. So then the first thing the processor can do is fetch a bunch of instructions. So in this case, in this execution, the processor has chosen to fetch 3 instructions. This is a bit non-deterministic. It's a choice. It could also have fetched 2 or 4. And we'll come back to these choices later. At the moment, I'll just make a choice here. So let's fetch 3 instructions. Then once these instructions are in the reorder buffer, the processor can execute them in any order that makes sense, right? For instance, it could execute this one or this one. And for this particular execution, I've chosen to execute the first instruction. Important to note here is that when we execute instructions in the reorder buffer, the results stay in the reorder buffer. They're not yet visible at the architectural level. So the instruction I is not yet updated. That only happens on a commit step. So when the oldest instruction in the buffer has completely executed, then we can commit it to the architectural state. And that's what happens here. The instruction retires, so gets removed from the reorder buffer, and the effect on the register is made visible to software. Right? So that's called the commit step. So now we've seen fetching, execution, and commit. So now let's look what happens for speculation. So let's fetch an additional instruction. So when we fetch an additional instruction, we get a branch. And that's interesting because at this point, when we fetch this branch, we don't know yet whether it will be taken or not. It will be taken if R0 is 0, but R0 will still change because of this instruction, and we haven't executed that yet. So at this point, we don't know whether it will be taken. So we have to guess, we have to speculate. And in this example, we speculate that the branch will be taken. So we say the program counter will become 5, but we remember that this is a guess, a speculation, by tagging the instruction. And this is the way in which in-flight instructions can be different from regular instructions. So some of them might be speculative instructions. And a speculative instruction or a speculated instruction, we tag them with the address of the original instruction. So the 3 here points back to this instruction that we can then use later on to check whether the speculation was correct, yes or no. Okay, so let's look at both the case where we do a correct prediction and an incorrect prediction. So let's first continue with the prediction that the branch was taken, and this prediction will turn out to be incorrect. If we predict this and we continue fetching instructions, then the next instruction to fetch is this 5th instruction. We can put it in the reorder buffer, and then we can start executing some instructions. For example, this one, and then this one, and then this one. So this loads from memory. I'm not showing memory here, but we assume that at address 12 we find the number 7, for instance. And then once these oldest instructions are completely executed, we can commit them to the architectural state. So these are 2 commit steps. We commit N7 and R01 to the architectural state. And now we can check whether this prediction was correct, yes or no, right? So before committing this speculated instruction, we should check whether the prediction that we did is actually correct. So we know the value of R0, it's 1. We should have branched if R0 was 0. That's not the case. So unfortunately, we mispredicted. And what will happen in this execution is that all this gets thrown away. This is called a squash or a rollback. All these results in the reorder buffer will be thrown away, and the program counter will be set to the correct value, which is 4, and we have to restart essentially. Right? So one interesting thing to remember that will be important for security is that in this scenario, when we have an incorrect prediction, it can happen that an instruction, for instance, this one, gets executed and then later gets squashed, gets thrown away. That's what we call a transient instruction, or that's what we call transient execution. And we'll see that that has some serious security consequences later on. Let's also quickly look at what happens with the correct prediction. That's not important for security, but it's why we do speculation, of course. So suppose we speculated that the branch would fall through, so it would go to 4 and not to 5. Then fetching would mean fetching these 2 instructions. And then we can execute them, and then we can execute the first 2, and we can commit these 2. And now we can again check whether the prediction was correct. And in this case, of course, it was correct. And so now we win time. We can commit, rather than squashing these results, we can commit all these results. And we can immediately go to program counter 6 to the rest of the program. And we have actually gained a bit of performance by doing the speculation. Okay. So I hope with this example you have an idea of how speculative and out of order execution work in the model that I'm using here. One thing that I want to point out again is that with this speculation and out of order execution, the processor has to make some choices. For instance, will I predict that a branch will be taken or not? And another aspect that's important, another aspect that attackers will exploit is the fact that they can influence these choices by the processor. For instance, a processor will predict whether a branch is taken or not based on heuristics and the past behavior, things that it has seen in the past. So an attacker can influence these predictions, for instance, by doing a lot of branches that are taken, that might cause the processor to also predict a victim branch to be taken. And this influence of the attacker on the branch predictor is called sometimes training or poisoning the branch predictor. And we should, of course, model this some way, right? And that's what I'll look at now. So now I will look at how in the processor model that we have, how we can model the attacker. And actually, transient execution attacks build on 2 kinds of attacker capabilities. The first is we will use classic microarchitectural side channels or covert channels. So things like cache attacks. I don't want to go deep into cache attacks, but essentially what these classic microarchitectural attacks make possible is that an attacker running code on the same platform as the victim can observe some of the victim's computation, right? And we will model that in a very simple way using what is called this constant time leakage model. So essentially what we will do, and I'll give an example on the next slide, is we will extend our model of the processor by just admitting that when a victim is executing, certain aspects of what it's doing are broadcasted to the attacker. And this is just a simplified model of the fact that an attacker who has code on the same processor in another virtual machine, for instance, might learn something about what the victim is doing through a cache attack, right? But I don't want to think about cache attacks now, I want to think about transient execution attacks. So what I'll do is I'll simplify the fact that things like cache attacks are possible by having this constant time leakage model. And I'll give an example on the next slide. So that's one thing we need to model. There's a second thing we need to model, which is this influence that the attacker has on the choices that the processor makes. And again, we will over approximate and simplify here by just giving the attacker full control over any of the non-determinism in the processor. So whenever the processor has some choices, like I can predict taken or not taken, or I can fetch 2, 3, or 4 instructions, whenever the processor has a choice, we will assume that the attacker can make the choice for the processor. And again, this is an over approximation of what the attacker can do, but it's also a simplification. And if in this over approximation we can still prove security, then of course it means that in the weaker reality where the attacker doesn't have full control but only partial control over these things, that anything we can prove secure under the strong attacker model will also be secure under the weaker attacker model. Okay, that's the big idea of how we'll model attackers. So I'll look at these two things, the constant time leakage model and this control that the attacker gets in the next 2 slides. So here is how we model the constant time leakage model. Here you see again the execution of the program that we looked at in the beginning of this talk. So what we do to extend the model with the fact that attackers can observe what the victim is doing through classic microarchitectural side channel attacks, what we do is we label each execution step, and these are the yellow labels here, with anything that the attacker could learn about the execution. And the things an attacker typically can learn are the control flow, so the value of the program counter. Why? Because the attacker can do an instruction cache attack against the victim, for example. And in that way, the attacker can learn the control flow. So we're just going to assume that our victim gives the program counter to the attacker on every step. Similarly, whenever a load or a store happens, so when the victim is accessing memory, like in this step here, the address from which something is loaded can be learned by an attacker through a data cache attack. And so again, what we'll do is we'll just assume that the victim gives the address that it's accessing to the attacker. So again, we put it in the label of information that is being broadcasted to the attacker. Okay, so that's the constant time leakage model. This is an old and well-known model, and so this is, for instance, what cryptographic code today already protects against. So cryptographic code is typically written to be what is called constant time, and what that means is the code will make sure that none of the secrets, for instance, the cryptographic key, will not flow into anything that gets sent to the attacker. So the control flow and the addresses that you access should not depend on the secrets that you want to protect. When a program has that property, it's called the constant time program. And before transient execution attacks, these programs were assumed not to leak any valuable information over microarchitectural channels. So in examples that I'll give you in a minute, I will sometimes make the presence of these leaks obvious by using a pseudo instruction leak V, which you can think of as any machine instruction that would broadcast something to the attacker. So for example, a loading from a certain address will broadcast that address. So that's a good implementation of this leak. Or jumping to V would be another implementation of leak V. This is just to make the examples, to make it very obvious in examples where stuff will be leaking. Okay, that's the constant time leakage model. So now we still have to model this attacker influence on the execution. So as I said, the processor sometimes has to make choices, and it has to make these choices, of course, within certain constraints, like you can fetch only if you still have room in the reorder buffer, or you can only execute an instruction if all the dependencies of the instruction are satisfied. But in general, the processor has a couple of choices at each execution step, and we're just going to assume that the attacker can pick whatever any of the choices that is possible. And here is an example again. So here we have again this execution that we looked at a couple of slides back. We see that in the first step, in the initial state, the processor really has no choice. All it can do is fetch instructions, right? There's nothing else to do. So there's only one choice. So the attacker has to choose fetch. The yellow arrow illustrates the choice of the attacker. So we do fetch, we do 3 times fetch actually. So we get 3 instructions in the buffer. And at this state, there's actually quite a bit of choice. We could fetch a 4th instruction, or we could execute this one, or we could execute this one. We can't execute this one yet because the dependencies are not yet resolved. So that's not ready to execute. So there are 3 choices here. And again, we give the attacker the choice. And in this particular execution, the attacker says, let me choose to execute the zeroed instruction. And that's what happens in this step, and so forth and so forth, right? So whenever there's a choice, the attacker gets to choose. And then in order to prove the security of a certain program or the security of a certain processor, what we'll have to show is that for whatever choices the attacker makes, no secrets leak, right? And if we succeed in showing that, then we have a strong security argument. Okay, with that, we have all the material we need to model the attacks. So if anything is unclear, the examples are a good point to ask questions. So I'll walk you through maybe at least 1, maybe 2 examples, depending on how we do on time. So in order to model transient, or to give you examples of transient execution attacks, we'll of course rely on these transient instructions that I mentioned, right? So we've seen that instructions can execute in the reorder buffer and then get squashed. Now this impacts security in 2 ways. One, these transiently executed instructions, they also broadcast information to the attacker over microarchitectural side channels. And that's actually very surprising. These are instructions that you don't expect to be executed. They're never architecturally executed, and yet they are sending information out. So that's something we will have to take into account. And secondly, and maybe even worse, transiently executed instructions can sometimes access information that you don't expect to be accessible, right? For example, it might be that you have access to memory that's protected by software, but on a misspeculated path, that protection might fail. And that's an example of a Spectre attack, and I'll give detailed examples on the next slide. So I don't want to say more here. It might even be that transiently executed instructions get access to information in another hardware protection domain. So some processors, as long as an instruction is still in the reorder buffer, might give it access to, so for instance, user code might give that user code access to kernel memory, right? And only at the point where the commit happens, an exception would be thrown, right? So these are called meltdown style attacks, and I won't talk about these today. But these are, in a sense, even worse from a security point of view. They're less interesting from a research point of view because they're easier to fix. So meltdown style attacks are being fixed in hardware, and will probably be gone in a couple of years. Spectre style attacks are a bit harder to defend against well, and so that's why I want to focus in this talk on Spectre. So let's look at a couple of Spectre examples. So what I want you to look at when I show you examples, I always want you to think in the following way. So I will show you a program, a memory, a program state that has secrets, right? And then I will show you a program operating on that memory. And I want you to check that the program is secure. Secure in the sense that if you think about the program architecturally, if you don't take into account out of order execution and speculation, the program will not leak any secrets, not even over the constant time leakage model, right? So before we learned about transient execution attacks, these programs would be considered completely secure, right? In fact, all the examples I'll show you are what are called constant time programs. So they were hardened against classic microarchitectural attacks. But then, and that will be the key point, of course, for each of these programs, if you have speculation and out of order execution, the secrets will leak anyway, right? And that's what makes these actual transient execution attacks. So let's look at 2 examples, maybe to avoid running out of time. So this is the classic Spectre v1 that probably many of you have seen or in one form or another. So this is how it looks in our model. So you see here a memory that has some public data structures, like a public array A with a length 2. And somewhere else in memory, it has a secret that I marked in red here, where I put it right next to the array, but it could be anywhere in memory. The attack would work wherever you put it. And then we have a program that operates on this program state, and the program does not, architecturally speaking, is secure, right? So what does it do? It accesses an element of their array A, but it does that under a bounds check. So this will always be an inbound access. So that means it only accesses public data. It doesn't access any secret data. And so the fact that it leaks it on a microarchitectural side channel doesn't matter. So this program doesn't leak secrets over classic microarchitectural channels. Yet, of course, if we do out of order and speculative execution, it might leak. Here's an example of how it could leak. So the attacker first fetches a bunch of instructions, and that will require the attacker to make a prediction on whether this branch will be taken or not. And of course, the attacker will cause a misprediction. We see that in this state here, the index is 2. So 2, 0, 1, 2 would be an access out of bounds. So in an architectural execution, the then branch would not be taken, but the attacker will predict that it will be taken to launch a transient execution attack, right? So we see the prediction that the branch will go to instruction 3. So then we have these in-flight instructions, and now the processor can execute any that are ready to execute, and the attacker can choose actually. So the attacker will choose to first execute this one. So this will load from address 3, right? This will actually be an out-of-bounds access. Here you see an example of where an instruction in the reorder buffer accesses a part of memory that you wouldn't expect to be accessible, right? And it loads that value, the secret value in this case, into register R0 in the reorder buffer. And then the next instruction that could be executed is this one. So this is actually the leak instruction. So it will load from an address R0, which means that also this value of R0 will be broadcasted to the attacker. An attacker could learn that value through a data cache attack, for example. So at this point, when we are at this point in the execution, the attacker has the ability to learn the secret. And of course, if we continue the execution, at some point, the processor will notice that this was a misspeculation, and then these two instructions will be squashed. So the bad instructions are actually transient instructions. They never will commit, but it's too late. The secret has already been broadcasted and is known to the attacker. So this is the essence of Spectre, and this is the classic Spectre v1. And then there are several variants of Spectre, and let's look at one more. And I want to the other examples to not run out of time. So here is an example of Spectre v2, or a Spectre branch target buffer. We again see a program state where we have a secret somewhere. And now we have a piece of code that operates on the secret. So we see that we load the secret, then call a function through a function pointer, and the function pointer points to address 20. And here is a very secure function that just overrides the secret and returns, right? The code is a bit oversimplified, but I hope you see the gist. So we load the secret, jump to a secure function and return, and nothing bad happens. So this code, if you execute it architecturally, won't leak. It will compute with the secret, but it won't leak the secret on a microarchitectural side channel. So this is a very simple model of what crypto code could be like. It computes on a key, but it will make sure to not use that key in a way that leaks over microarchitectural side channels. Right? But yet again, if we have out of order and speculative execution, things can go very wrong. So for example, what an attacker could do is start fetching instructions, and that will require a prediction of this branch, because this function pointer will not be known yet, so a prediction is necessary. The attacker can choose the prediction, and the attacker will choose the prediction to be something anywhere in code memory that contains a leak gadget, right? So for instance, maybe at address 31, there's an instruction that would leak R0. So then the attacker will predict the program counter to go to 31, and then we can execute. We first do the load, the secret goes into the register. It can even be committed, so the secret is now in an architectural register. And now the attacker can choose to execute this instruction, and this will broadcast the secret again over a microarchitectural side channel, and the secret is now in the hands of the attacker. And of course, as in the previous example, a bit further on, the processor will notice that this is actually a misprediction. It should have been 20. The function pointer will actually be 20, not 31. So this will be squashed, and again, it's a transient execution, transient instruction that has leaked the secret, but it's too late. Even if we squash it now, the secret is already in the hands of the attacker. Okay, and there are other variants, so I'm going to skip some of the other examples. If you want to know more, if you want to see more examples of transient execution attacks, this site, of which I gave you the URL also a bit earlier, with the classification tree, for each of the variants of the attacks kind of gives you a simple summary of how the attack works, and then gives you references of papers that describe the attack in detail. Right. So I'm going to point you to that site for more examples. I want to use the last 15 minutes that I have to talk about defenses. So how should we address this? So how can we avoid programs leaking through these transient execution attacks their secrets to attackers? Well, there are two kinds of defenses that are interesting to look at. So first are software-only defenses, and we'll need these for a while, right? All processors that are out there are Spectre vulnerable and have not yet any countermeasures against these attacks built in. So we will need ways of writing programs that do not leak across these transient execution attacks. And we'll need to do it in software because updating the hardware will take a while. So if we look again at the Spectre v1 example that we just looked at, this might already give you some ideas on how we can solve this in software. So the key problem with Spectre v1 is that if we have a misspeculated branch like this one with an indexed array access, on a misspeculated branch, this index might go out of bounds. So what we can do, one of the countermeasures is to make sure that even on misspeculated branches, all memory accesses are still fine. And a very simple way of doing that here would be to insert a modulo computation in the then branch. This for the architectural execution, this is not necessary. If I is between 0 and len, then this modulo operation does nothing. It's really a no-op. But on a misspeculated path, if I is bigger than len, on a misspeculated path, this will make sure that even on a misspeculated path, the index I will always be in bounds. And here you see an example execution. So the difference with the previous execution is the dangerous instructions, the loading and the broadcasting, the leak instruction, they now can only happen after the modulo instruction has executed. Why? Because this instruction depends on I, and this potentially can change I, so the processor will not execute this before it has executed this. And as soon as it executes this, I will be in bounds. So of course, a 3 will become a 0 with the modulo computation, or a 2 will become a 0, I should say. So we're still accessing some random element of the array, but at least it's certain within the array, so it's certainly a public value. And we see that indeed what we now broadcast to the attacker is the value in slot 0 of the array, rather than the secret that we broadcasted when we were vulnerable to Spectre. So this technique is called, or generalizations of this technique are called speculative load hardening, and this is built into compilers today. So the disadvantage of it is that it is a bit ad hoc, and it's tuned mainly to just Spectre v1. So it's not a general solution, but it is one of the countermeasures that's being widely used as we speak. Another slightly more general countermeasure is insertion of fences. So a fence is an assembly language instruction that existed in processors more for concurrency reasons, for processors that have weak memory models, essentially to make sure that on concurrent execution, things didn't go wrong. But simplified a bit, you can think of a fence as blocking out of order execution. I'm oversimplifying a little bit, but that's how you can think about it. So a fence will have as a consequence that the processor will not execute instructions behind the fence until the fence is committed, right? And of course, we can use that to protect against speculative execution attacks. So if we put a fence right after this branch, so here we see the fence also in the reorder buffer when the attacker fetches all instructions. So now the consequence of this fence instruction is that these two instructions cannot be executed until the fence commits. So that means that the attack is not possible. The fence will actually never commit because it's behind a misspeculated branch. And so these instructions can never execute, and the vulnerability is closed, right? So that's great. But the big downside of this is that it has a big impact on performance. So essentially, by putting a fence here, we we essentially turn off speculation also in the case of a correct speculation, right? If the branch is correctly predicted to be taken, the fence will make it impossible for the processor to out of order already start executing code in the branch. And so the performance cost of inserting a fence is non-trivial, is quite high. And so what people are doing in software defenses now is trying to come up with ways of placing these fences in very smart ways, so placing as few as possible of them, so that the performance cost is reasonable and we still are secure.
So here I have one question, Mark, here. So
yes.
I mean, this solution, I mean, answer will have for sure, I mean, all overheads, right? Yeah, right.
Yes.
Yeah. And I mean, the first one, I mean, what you showed, like the load, speculative load hardening. I guess it should be applied aggressively, right? In a much more consistent way to ensure, I mean, some comprehensive protection, right?
Yes. So indeed, if you want to be secure, it's very good to apply either of the two software defenses that I mentioned here aggressively. The more you do of it, the more security guarantees you have. But of course, the more aggressive you do these insertions of defensive instructions, the more performance cost you will pay. So that the trade-off here is unavoidable. And I'll give a pointer. So this is actually a very active area of research. How can we do this in a way that performance cost is minimal? And there's a good survey paper at SMP the last year, SMP 2022, that surveys like all the approaches to minimize these fence insertions.
Mm-hmm. Okay.
So I'll point out the reference when we get to the conclusion slide.
I have another question. Could the fence be coupled with dependency constraints to come up with a better placement?
Yes, that's a very good point. So that's again one of these optimizations that people are looking at. So for instance, it might make sense to place this fence later if you see that there's no danger of anything leaking, because there are some dependencies, so some instructions will have to be executed first, and that might make it possible to put the fence a bit later, for example. You could also notice if you have code like this, for example, where this I is dependent on this I, and this I will make sure that the index is inbounds anyway. If you would originally have code like this, then you don't need to insert the fence, right? So it might be that the code, because of the way in which it is written, because of the way in which it is written, may not need a fence, but then of course that's kind of program analysis, and they need to do some kind of formal reasoning about how the code will behave to be sure that you really don't need to place the fence. And that's exactly what in the research community on software defenses people are trying to do. So they're trying to come up with verifiers that can check that if you put very surgically in some places in the code a fence, that can show that you can't reach a potentially dangerous leak.
Okay, thank you.
Okay, so these are the software-only defenses, and I think everybody agrees that these pure software defenses will be important for quite a while. So this is something we won't we will be needing for at least 10 years in the future. So it's a very important area of research, but I think we also start to see that they have an unavoidable cost, and that better defenses can be obtained by also changing the hardware a bit, right? And so one promising area, and now I'm moving into today's research essentially, is to think about what kind of so it seems very hard to redesign a processor to be completely resilient to Spectre, but still have all the benefits of speculation. So what people instead are trying to do is come up with hardware that provides secure speculation for specific security policies, right? So what that means is, suppose you have software that complies with a specific security policy, then I can reason about that policy just not taking into account out of order or speculative execution, just thinking about the architectural semantics. And if I prove that the code has that policy, then I can run it on a speculative execution enabled processor and not introduce additional leaks. So in other words, as far as this one particular policy is concerned, this processor allows you to ignore all the issues surrounding speculation. And so two examples of this are, for the sandboxing policy, Marco Guarnieri and others have shown that there are hardware extensions that you can put in the processor such that if software complies with the sandboxing policy, which means it can't access memory outside of a certain well-defined range, then you can run that software on a speculating processor with these countermeasures, and no additional leaks will be introduced. And similarly for the constant time policy that we talked about in this talk, so if code satisfies with the classic constant time policy that most crypto code today already satisfies with, then we can build processors that will not introduce leaks because of speculation, that still can use speculation very aggressively and usefully, so they have good performance, but they will not introduce leaks as we saw in the examples before. Right? And so here are a couple examples of papers that do that, and the one I want to talk about in the last 5 minutes is this is a paper from my own group, which essentially builds such a processor with a full proof of security. And I want to just briefly explain the basic idea behind this processor. So this is a paper that will appear at Usenix Security, but there's already a technical report online if you want to read more details. So what's the basic idea of this processor? So it will be a hardware-software co-design. So the software will have to do something. In particular, the software will have to make sure that it's constant time, right? If you think again the Spectre V1 example, that code was constant time. So let's use that as an example. And then there's a hardware part, and the hardware part is that the processor will need to know where secrets are in memory. So the things that I marked kind of for illustration as secrets on previous slides, now we want the hardware to be aware of that. In our prototype, the processor has a couple of registers that you can configure to indicate beginning and ending of regions in memory where secrets are stored. So for example, you could indicate that at address 3, there's actually a secret. And the good thing about that is once the hardware knows that, if you are doing an execution, these secrets can be tracked. And so that's the second hardware extension. The microarchitecture, so the processor, the processor that is using this reorder buffer should track secrets whenever they enter the processor and should track them throughout the reorder buffer. So for example, this load, when it loads from this cell in memory, the processor will know that it has loaded from a secret memory cell. So it will mark this secret also in the reorder buffer as secret. And when that value is then used in this load, it will also mark this load as containing a secret, right? So this is classic taint tracking, but at the hardware level, so that at any point in the reorder buffer, we know where secrets are being manipulated. And then the final part that the hardware needs to do is whenever there's an instruction that could potentially leak something, and so the processor designer will have to mark instructions as safe or not safe, depending on whether they can broadcast something to the attacker. And whenever there's a danger instruction, like a load, the processor should refuse to execute it under a speculative shadow, so while it's still speculative, if it contains a secret. So this is like a very lazy way of inserting fences. You could say at the point where we notice that a secret is about to leak, we will at the very last minute insert a fence here and refuse to execute this instruction until it becomes non-speculative. That's the basic idea, and I hope you can see, well, you can see on this example that at this point the attacker doesn't have the choice to execute this because it's tainted and it might leak. So it has to execute the other instructions first, and at some point the misprediction will be detected and this will be squashed. And again, the result is that this is secure. Okay, so let me summarize what we did on this. So with this, I think you have the general idea of how such a hardware-software co-design could work. What the paper, and here is a URL where you can find the paper. You can also find it by Googling it. What the paper does is it proves this fact that if you run constant time program on prospect compliant hardware, that then nothing leaks. Right, that's one contribution of the paper. We also do a full implementation in an out of order RISC-V core, and we actually make the processor open source available. So both the vulnerable baseline processor as well as the processor that has been made prospect compliant is available as on the web, open source. You can put it on FPGA and play with it if you want. We also experimentally evaluate the performance cost, and I don't have time, I see, to discuss that in detail, but one important point that I want to make is that if you mark the secrets in memory precisely, right? If you mark, for instance, for a cryptographic piece of code, just the key, and the cryptographic code is actually constant time, then you pay no performance cost. Whether you have prospect on or not, the performance is exactly the same. And that's not that hard to see, because for constant time code, constant time crypto code, the only way in which a secret could leak is on a misspeculated path. On an architectural path, there will be no leakage because the code is constant time. So that means that prospect will only block misspeculated instructions, and that doesn't cost you anything in performance, because the misspeculated instruction is wasted time anyway. So that's a very nice property of this hardware software co-design. Of course, if you have non-constant time code, or if you mark more of memory as secret, for instance, if you mark all memory as secret, then you start paying a performance price. That's unavoidable. So with that, I reach the conclusions of my talk. I hope I convinced you that transient execution attacks are an interesting and fundamentally new class of attacks. They break many important security mechanisms like virtual machine isolation, software-based sandboxing, and so forth. They're not easy to defend against, and we've seen a huge outburst in papers looking at attacks and defenses in this area. I've shown you the 5,000 citations of the first 3 papers. We have these short-term defenses already deployed. It's amazing how quickly the hardware-software ecosystem has reacted to these attacks. So compilers have been updated, processors have been updated with microcode, but all existing defenses have important downsides. So long-term defenses are the subject of current research. You have these pure software defenses that I mentioned, and this is the paper that I mentioned a bit earlier in the talk. So this is a great overview paper of the state of the art in software-only Spectre defenses, including things like, can I place my fences a bit more surgically, for instance. So that's one line of research that will be very important for years to come. But then you also have more hardware-software co-design approaches, and 2 starting points to read more. There are plenty of designs out there, but 2 good starting points are, I think, maybe the paper by Marco Guarnieri, who kind of was the first to show how to handle this formally, the hardware software contracts approach. This received the best paper award at Security and Privacy 2 years ago. And of course, it would be great if you also take the time to look at our paper on the prospect system. So I think we have the first synthesizable processor that's provably secure against Spectre for constant time code. And it also kind of many of the examples that I used in the talk are also part of that paper. So if you want to look back at them, this is a good place to go to. With that, I think I'm already 3 minutes over time. I apologize for that, but that's all for me.
No problem, Frank. Thank you so much. It's quite interesting. I want also to see the paper right now. I'm exploring it at high level. It's quite solid, and it's quite let's say quite research. I think, as you mentioned, we don't have that much time. Most of the questions, I think, we got them during the talk. I would like to thank you again, Frank.
Okay.
And yeah, keep in touch.
Yes, thank you very much for the invitation.
Yeah. Well, just I think there is one additional question. Yeah. Sorry. So there is one additional question before closing the session. So, is the hardware solution implementation of HSM style, where the speculation results are accessed only through some policy?
Yes. So yeah, that's a good analogy. It's not exactly the same as a HSM style, but you can. So essentially, what the processor implementation does is it will allow the pipeline to access secrets in any way, but it will track them. So whenever secrets enter the processor, all storage elements in the processor have a taint tracking tag that marks secrets. And so the processor will at any point be aware of where the secrets are. And then you can think of our enforcement mechanism as saying, indeed, under speculation, you cannot certain instructions cannot access secrets. So the instructions that could broadcast a secret, like a memory load, things that broadcast secret because of the possibility of things like cache attacks, these instructions are not allowed to access anything that is secret. So I can see the analogy. I think it's a good question. I can see the analogy to HSM style enforcement of policies, except here, of course, it's a very hard-baked policy into the processor. It's not something you configure. Well, the only configuration you do is where in secrets are where in memory are the secrets. That's the configuration you do. Wow. And I see the second question. Share the implementation. Yes, absolutely. So let me go back. So if you find our paper on archive, it has a pointer to the GitHub repository. The unprotected processor is already online. The repository with the protected processor is also there, but it's still being updated. So the paper just got accepted 2 weeks ago, so we're still updating it. So if you want to look at the code, wait a couple of weeks. But
yeah.
Sorry?
No, I said I shared the paper in the chat. If anyone.
Okay. Yeah. So it's just on GitHub. So if you look for the name of the defense is Prospect, the baseline processor is called Proteus. If you search for this, you'll also find, and if you don't find it, send me a mail. But so the URL to the open source implementation is in the paper.
Good. Thank you very much again, Frank. Thank you so much, and keep in touch.
Okay, thank you very much for the invitation, and see you at some future occasion.
Yeah, thank you so much. Bye-bye.